So again, you have 2 weeks for finishing up the homework. It might take up to 2 weeks, depending on your skills. If you know how to program, might be taking you half an hour. To us, it takes a couple of hours to finish the thing. Again, depends on your skills, right? So start early, so you finish early, perhaps, or perhaps you just take the whole 2 weeks, but up to your skills. All right, I just eclipse and I leave Yann to give his lectures. Bye-bye.
Okay. So the first one is a value. We already talked about it. This is the positive part function, sometimes denoted with kind of a superscript plus, which is really just a max of 0 and x. Okay, so it's a function equal to 0 when x is negative, equal to the identity when x is positive. It's not everywhere differentiable because it has a kink, but as I explained, when we backpropagate, we just define the gradient as a subgradient, which is a perfectly fine mathematical concept. But there are variants of this. And one issue with the ReLU is that when you're in the flat part, there is no gradient being backpropagated through that particular nonlinearity, right? So if the weighted sum coming into, or whatever value coming into a ReLU is negative, that ReLU, when you backpropagate through this, will just produce a 0 as the gradient going through it, because it's flat, right? You can change the input, it doesn't make any difference to the output. And that sometimes can be a problem. So people have come up with this other thing, the ReLU or PReLU or things like this. And they're basically versions where the negative part also has a slope, which can be trainable or can be adjusted or can be set randomly. It's a good idea to have a function that has only one kink, because, and that's probably one reason why ReLUs and PReLUs and things like this have become so popular, is because they're basically equivariant to scale. So what does that mean? That means that when the input is multiplied by 2, the output is multiplied by 2, but otherwise unchanged. Okay? I think in mathematics, that's also called homogeneous. So the advantage of this is that a ReLU doesn't care about like the amplitude of the variables that come into it, right? It will fulfill its function regardless. Whereas if you had a function with 2 kinks, then it really matters. The amplitude, the amplitude of the input signal really matters, because it will determine whether you're using the 2 kinks or only one, for example, right? And that seems to be an advantage, particularly in very deep networks. Right, so the PReLU, so the leaky ReLU has a small negative slopes, which you can barely see here. The PReLU has a coefficient A here that determines the slope in the negative part. These are still contrast equivariant functions. So here's one that isn't contrast equivariant, or isn't equivariant to scale, to amplitude, if you want. And it's soft plus. So you can think of this as kind of a soft version of ReLU. And the sharpness of the kink is determined by a parameter beta. So this function, log of 1 plus exponential beta, right? When beta x. When x is very large, the exponential dominates the 1, and the log cancels the exponential. So that basically becomes the identity function, right? The 1 over beta cancels the beta. And for x negative, then exponential something negative is close to 0. So this becomes log 1, right? And that's basically 0. So you can tell that this function smoothly transitions between basically being close to 0 to being close to the identity. And the speed of that transition is this beta parameter. So if you have large beta, it looks very much like a ReLU. It's a little soft at the corner, but it's very much like a ReLU. If you have small beta, then it's a smoother transition. That's nice. It's sometimes used as a cost function as well. I'll come back to that. This is a different way of making the ReLU soft, and also have a bit of a sort of negative value, which may be interesting in some cases. So, as I said, I'm not going to go through the entire list of all of those variants. You're welcome to play with them if you're interested. There's sort of various parameterized function that kind of make a value kind of look more like a linear function or look more like a hard value. Things that have funny values for parameters that kind of try to stick two pieces together. Lots of variations. Now this one, I'm showing this one because this one is not monotonic. It sort of goes down a little near zero and then goes up. It's generally dangerous to do this because if you have a non-monotonic function, it means there are several possible input values that will give the same output values. And backprop doesn't like that very much because that is probably going to create some sort of saddle point or local minimum or something. So people tend to stay away from non-monotonic function. They don't have to be strictly monotonic, but a monotonic function is a good idea. Okay, so this one is kind of a double, saturating function, which in this case has the threshold at 6. Why 6? Why not? This one is is used actually fairly widely, so it's useful to to know about that one. It's called the sigmoid function. Physicists actually call this the Fermi-Dirac distribution. If you put a beta parameter inside of the parenthesis. And it's a very well-known function. It's sometimes called the logistic function as well. So it's a function that is equal to 1 when x tends to, in the limit of x going to infinity, and equal to 0 when x in the limit of x going to minus infinity. And it sort of smoothly transitions between the two. Okay. So if you want some binary variable in your network, a switch, for example, something that decides, A or B or something, right? Like an elementary classifier, but you want this thing to be differentiable. This is a good function to use, all right? Because it will smoothly transition between 0 and 1. We'll see in a minute that if you want to activate a particular part of the network and, or deactivate it, this could be a good way to compute a coefficient with which to activate or deactivate a part of the network in a differentiable manner. Right, so keep this one in mind because we're going to use it. This is essentially the same function as before, except it has a different name, and it goes between -1 and +1 instead of 0 and 1. But it's essentially the same function, except you multiply it by 2, and you shift it by 1, and then there's a coefficient on the x, which I'm not going to go through. It's called the hyperbolic tangent. It's also very popular. This was the standard function that a lot of people were using in neural nets, going back to the 1980s and 90s. Most neural nets were using functions like this and not using ReLUs. ReLUs are actually a fairly recent development, less than 10 years, about 10 years. And it turns out ReLUs are better because of this equivariance to contrast. They're better when you have very deep networks for some reason. We don't fully understand why, actually. From the theoretical point of view. But experimentally, you can train much deeper networks with ReLUs than you can with hyperbolic tangent. So hyperbolic tangent, you can compute it this way, but most numerical libraries have just a call for hyperbolic tangent that you can use. And the advantage of this function is that because it saturates, it bounds the values that your network can take, which is good in many ways. But it has a disadvantage, and the disadvantage is that if the variable that goes into the hyperbolic tangent is very large, then you get into the flat spot of this hyperbolic tangent, and you basically get no gradient. When you backpropagate gradient through that module, you don't get much of a gradient at all. And so for the same reason, the flat spot of the ReLU can be a problem. Here you have two flat spots. And what's more, the amplitude of the input variable will influence how much of the flat spot you hit during forward propagation. This may be why those using those functions basically limits how many layers you can have, because one of those layers is going to hit those flat spot because the weights are too large or something, and that's going to kill the entire network. Essentially, you're going to get vanishing gradients below that. And you don't have this invariance to scale. One advantage of this over the sigmoid is that it's symmetric. And for the same reason I explained last week, that it's a good idea to normalize the variables of a neural net so that they have zero mean. It's also good for the internal variables of a neural net to have more or less zero mean. And so a hyperbolic tangent will produce variables, state variables, neuron outputs that, essentially have zero mean. Not necessarily, but, they have a good chance of being centered around zero. Whereas with a sigmoid, or a ReLU for that matter, there's no chance at all that they will have zero mean, well, because they are strictly positive. I mean, not strictly, but they're positive. So because of this saturation problem of the sigmoid and the hyperbolic tangent, our friend in Montreal a few years ago proposed this other kind of smoother function that doesn't transition as fast and still has a slope when it saturates. It's called the soft sine. So it's x over 1 plus absolute value of x. This is, I believe, a paper by Xavier Gloro and Yoshua Benjo. And, that has some advantages. So some people use it. Hard 10H, this should really be called a ramp, saturating ramp. So this is just a saturation function, right? It goes between -1 and 1, and it's linear in between, and there is two kinks. So it has, again, the disadvantage that it's not scale invariant. So then you have weird functions that don't tend to saturate, but they sort of bring the value towards zero, right? So this is a function that if you give it a small value, it will basically return something that's really close to zero. And if you give it a bigger value, it's close to the identity, minus or plus a constant. So this one is called the 10H shrink, and it's the difference between the identity and hyperbolic tangent. It's kind of a hard version of it called a soft shrinkage. This is used in sort of very weird cases that we may talk about when we talk about unsupervised learning, in sparse coding in particular, and hard shrink. But this one, you don't want to use it with backprop because it's not even continuous. Okay, then you have kind of, variations of those. So this is the log of a sigmoid. Why is it good to have a log of a sigmoid if you have the sigmoid and the log? The reason is because of numerical instabilities. So it's very often the case that you will have functions with exponentials in them, and then you want to take the log of them. And if you write them in PyTorch as two different modules, one that computes this function with exponentials and one that takes a log, you're going to get numerical instabilities. There is some values of the input for which the output will be almost zero, and the log will basically want to be minus infinity. But if you do the computation in one swoop, and you can rearrange the term, you never get those numerical issues. So taking the log of a sigmoid is an example of that. Okay, now we're getting into modules that are not simple nonlinearities, but they're very important because they're used absolutely everywhere. But they're modules that turn a vector into another vector. Okay, and there's two of them, softmax and softmin. They basically are the same thing. They should really be called argsoftmax and argsoftmin, but historically they've been given the name softmax and the name stuck. It's really not a good name for that, but in fact, the inventor of that technique in the context of neural net is a guy called John Bridle, and he regret calling them softmax and softmin. He said I should have called them argsoftmax and argsoftmin. So they're really the same function, except one has a minus in it, and they're vector functions. Okay, so
Yann is frozen. Or is my computer frozen? Yes, my computer is frozen. No, Yann is frozen. Yann is frozen too. Okay, very good. So let me until he comes back. So like the documentation of Torch is huge. And then most of the time we get like people that are overwhelmed about like, oh, how do we use this? How do we use that? So the documentation doesn't really tell you how to use these functions. And so in we're trying now to briefly cover, like to just go over everything, such that whenever you're going to be looking at the documentation, because you're going to be looking at the documentation, quite often, at least you can navigate and figure out and understand why those things are there. Okay. Can you provide some examples that non-monotonic loss functions will lead to problems? I have no idea. That was the first time I hear about that. So we can ask Yann when he comes back. It's going to take a few minutes. He said, okay, fine, I entertain you for that for the moment. So that I don't know. Like I have no personal experience about non-monotonic loss functions. Can I address other questions? Why is ReLU considered when it's not differentiable? So, okay, this is actually so cool. If you have a neural net made of ReLUs only, you can actually show that the outcome of this network is going to be simply a piecewise linear interpolation of like several linear networks, okay? And so what happens is that like a given network will section the input space and apply a linear transformation from that input to the output, okay? And so there are no, like for the given patch, you're gonna have like a linear network, which is straightforward to train. And the only thing basically that you are doing during training is going to be like basically figure out where to position those patches and then what kind of transformation you would like to apply to those regions. Okay. But also like theoretically speaking, these ReLU-based neural net are much easier to analyze. ReLU is differentiable. Actually, yes, ReLU is differentiable. You had to use subgradient, yeah. But again, the issue with ReLU is that you have exactly zero gradient for the negative part. And then if you get in that region, also things don't move, right, with the gradient. So instead, we have to use, for example, leaky ReLUs. When we train, let's say, a generative adversarial network, which we'll cover towards the end of the class, such that you always have some gradients flowing through the network, okay? So again, ReLUs might give you some issues because of the zero gradient side. So we just give a small kink, like a slope, such that you still have gradients. And then there is a question for Yann. So can you hear me, right, Yann?
Yep.
Okay, can you mention a few issues about the fact of using non-monotonic activation functions? That it was not clear.
Right. So let's say you're using a non-monotonic activation function, something like absolute value, for example, right? So it's like the value, except it's identity in the positive part, negative identity in the negative part. So there, whenever the output of the network wants that particular unit to have a particular value, it's got two choices as to what the input should be, okay? And which one it chooses depends on just what the current value is. And this may or may not be good in the sense that, the gradient could take you in one direction or the other direction. Let's imagine that the nonlinearity you put is a sinusoid, okay, with multiple periods. There is lots of different places that the input can be that will produce exactly the same output. And so it doesn't pin down the value of the input. It just says, the input should be either this or that or that. And that creates local minima necessarily or saddle points, because it means there are several choices to get the same result, which means there are several values of the parameters that will give you the same output, which means there are several local minima, okay? So there is this sort of intuition that local minima are probably a bad idea, that saddle points certainly are bad. And so the more non-monotonic nonlinearities you put in your system, the more of those local minima or saddle points you're going to create. And that's probably bad.
Okay, and there is one more question. We've before mentioned that using those saturating nonlinearities are leading to possibly vanishing gradient. So isn't a ReLU perhaps leading to exploding gradients instead, since it's not saturating?
So not necessarily. Exploding gradient. Okay, the gradients would explode if. So, for example, imagine a network that has a single input, single hidden unit, etc. Right? So you're kind of repeating. It's a very simple network with basically a single hidden unit at every layer, right? And you stack the layers. If you put a ReLU at each layer, and the weight is 1, let's say, for every layer, you're not gonna, as you backpropagate, the gradient will say. And let's imagine the input is positive, so all the ReLUs and all the weights are 1, so all the ReLUs are in the linear region. When you backpropagate, the gradients will also be 1, right? Because you're going to get the gradient multiplied by the derivative of the ReLU, which is 1, then multiplied by the weight, which is 1, then by the slope of the ReLU, which is 1, etc. So the gradients are going to be 1 everywhere. Now imagine that the weights are not 1, but are 2, okay? So all the weights in each of the networks, in each of the layers, are equal to 2. So first of all, for an input equal to 1, after that you get 2, then 4, then 8, then 16, etc. Right? You get powers of 2 as you go up the layers. So you get an exploding state, and the gradient also explodes. So if you start with a gradient 1 from the output, you backpropagate through a weight equal to 2. So your gradient is now 2. And then 4, and then 8, and then 16, right? So you get a huge gradient here for the lower layers that have, which means the weight here is going to change a lot, and a relatively small gradient for the top layer, which means that weight is not going to change much. And so that's a bad idea. What you want is the amplitude of the states and the amplitude of the gradient to be more or less the same all the way through. And what people do to kind of enforce this today is they use a module called batch normalization or group normalization. I mean, there's sort of various normalization tricks to ensure that the activities of the units are more or less all the same. They have variance 1 roughly, right? So that's a way of kind of preventing this from happening. So the explosion is not necessarily going to be due to the ReLU. Like if you use an exponential for the nonlinearity, yes, you're going to get exploding gradients. But a ReLU just has a slope of 1, so that's not necessarily going to create issues. You can have that issue because of gains inside the network that are bigger.
Okay, can we take one more question?
We can.
Okay, so could the non-monotonicity actually be a good thing? For example, it could mean that there are multiple weight initializations which could work instead of getting stuck due to a bad weight initialization?
Yeah, that's right. So it's just that, again, you're going to have saddle points if you have those non-monotonic functions, and saddle points are bad. So it may work. Like it depends what type of function you're using. Not a huge amount is known about this. What is known is that with monotonic function, particularly with ReLUs, there's a little bit of theoretical results on why, the intuition that why they're good kind of translates into some very weak theorems on why they're good. But really, those are really complex systems with complex dynamics that people don't understand very well. Now, what you can think about a way to think about the ReLU is as a if you know anything about electrical engineering, is a diode. Okay, so it's like something that lets values that are positive but not negative, and this is sort of the most elementary way of detecting something, if you want, right? The most elementary way of detecting something that happens versus something that does not happen is if you have some sort of linear representation of it, is you have a threshold, and below that threshold, things are equal to 0, and when they're positive, they're positive. This is the basic principle of a radio, for example, right? You build a radio, and you want to detect the signal so that you can hear the audio and eliminate the carriers. you have to have a diode. You have to have a detection system. That's called a diode in electronics, and it plays the same role as a value. And Alfredo is going, oh, funny, I never thought about this before, even though I'm an electrical engineer.
That's the name. That's where the name comes from, right? The rectifying.
Rectification.
Yeah, rectification.
The diode is actually called a rectifier. More general term for it.
One last question, since this actually, I heard about this paper. Any thoughts about the Siren paper, the one that is using sinusoidals for the activations?
Oh, that's different. So it's not an activation. The Siren paper, if I remember correctly, right? So this is a paper by he's at Google, but he was at Berkeley for a while. Okay, the idea is that
Vincent Sitzman, Martel, Bergman, Lindell, and Betzstein.
Okay, these are not the names I remembered.
Okay,
but there was an earlier paper, I think, from the NERF people on like Fourier representations. Okay. So I think so I may be confused about what Siren actually had. The Siren paper talks about, but I think what it is that it's basically a pre-processing layer. So let's say you have a neural net that has a single input, a scalar input. Okay, and you want to compute some complex function of that single input. You could just build a neural net with a number of hidden units and several layers and put the output. But what they do is that one thing you can do, which seems to be very useful, is that you hardwire the first layer. So the first layer is basically hardwired, and it's very similar to the basis function expansion I was talking about last week, when I talked about like hardwiring the first layer. And what you do is you make this activation function for this guy be equal to a sinusoid. And for this guy, it's a sinusoid with twice the frequency. And for this guy, 3 times the frequency. And for this guy, 4 times the frequency, etc. Right? So you have activation functions that are, sinus x or some coefficient, sinus 2x, sinus 3x, etc. And for good measure, you also add the cosine. So cosine x, cosine 2x. So you basically expand the dimension of the input, right? And that's basically, that would be sort of a Fourier series expansion of your function. So it makes it easier then for the system to compute a complex function by basically computing weighted sums of those basis functions.
Okay. And finally,
polynomials, you can do this with all kinds of stuff. Yeah.
Finally, why are we covering all these activation functions in today's lecture?
We're not covering all of them. We're just covering the ones that people use.
Okay.
I put the slides for all of them because that's a good reference. But but that's basically you can find this in the PyTorch manual.
Yep.
Okay. So here's what I wanted to talk about. I wanted to talk about softmax, right? So by the way, my computer crashed when I tried to grab my little pen here, and I disconnected one of the connectors that has a USB to everything else, and it just completely crashed the machine. Sorry about that. Okay, so softmax is this thing. It's a module that has n inputs and n outputs, and it computes the exponential of each input and then normalize them by the sum of the exponentials of all the inputs, right? So, basically, let's say we have 3 inputs. These are the xi's and or xj, I should say, and these are the sorry, not the x's, but the z's. I'm going to call them zi. Okay. So zi is equal to exponential xi over sum over j of exponential xj. Right. So each of these guys, okay, is you take the exponential of the corresponding input and then you normalize by the sum of the exponentials of all the inputs. Now, what does that give you? It basically allows you to transform a bunch of numbers between 0 and 1 a bunch of numbers, the xi's, whatever they are, into another bunch of numbers, the z's, that are between 0 and 1 and sum to 1. Okay, so it's quite obvious that when you sum all the zi's over I, you're going to get 1, right? Because you're going to get the same thing on the numerator and the denominator. Okay, so the sum of the zi's is going to be 1. And they're all going to be between 0 and 1 because, of course, the sum of the exponential xj's is larger than exponential xi. So this is a way of turning, and we're going to use this absolutely everywhere, okay? So it's very important. So this allows us to turn, for example, a bunch of scores in some arbitrary unit into things that look like a probability distribution over a discrete distribution, over a discrete outcomes, okay? So here's a special case of this. Let's imagine that we only have two inputs. Okay, x1 and x2. So z1 is going to be equal to, e to the x1 over e to the x1 plus e to the x2. Okay, cool enough. Now let's imagine that x2 is always equal to 0. Okay, it's constant and equal to 0. Then this turns into e to the x1 over e to the x1 plus 1, because exponential 0 is 1, right? So if I divide by e to the x1 above and below, which means I multiply by e to the minus x1, okay, I get 1 because they cancel. Here I get 1 also because they cancel. And here I get e to the minus x1. And surprise, surprise, this is the sigmoid for the logistic function. Or as physicists call it, the Fermi-Dirac distribution. Okay, so now what we've just seen is that the softmax basically is a multinomial generalization of the logistic function. Or conversely, the logistic function is a special case of softmax for two variables where one of them is always 0. Okay?
And why are we using exponentials here as like our nonlinear function?
Because the exponential is a very simple way of smoothly turning a number from with any range from minus infinity to plus infinity into a positive number, right? There's many ways to do this, I would admit, but exponential is good. There are other deep reasons for this, okay? But which I'm not going to go into right now.
We say about this a bit in a future lesson, right?
Yeah, we'll talk about, basically when we talk about energy-based models and their relationship to probabilistic models.
Mm-hmm.
But, intuitively, it's a good way of turning a bunch of scores into a probability distribution. So if you are interested in having calibrated scores that are between 0 and 1 and sum to 1, if you want to do classification, for example, okay, you use a softmax module because you get whatever score come out of your neural net, and then you turn them into a bunch of positive numbers that sum to 1, and you can interpret this as a probability distribution over categories. Okay, why is it called softmax and what should it be called soft argmax? The reason is that if all the x's are very small, okay, let's say large and negative or whatever, let's say all the same values, and one of them is significantly larger than all the others, then what's going to happen is that the output is essentially going to be very close to 1 for that input that is much larger than the other, and it's going to be close to 0 for all the other ones. Okay? And so that basically creates a kind of competition, if you want, between scores. And the interesting about softmax is that softmax doesn't care about a shift in the variables. So if I take a vector x and I add another vector v to it, okay, a constant vector. I add a constant to every term, right? So this is not just a constant vector v; it's a vector that has the same value everywhere, right? So let's say I add c to all the components, right? And I compute the softmax of that. This is actually equal to softmax of x. Okay, so take a vector x, add a constant to all the inputs. It makes no difference to the output. So what that tells you is that softmax actually only cares about the relative values of the inputs, doesn't care about absolute values of the input. If your inputs are, between -1 and 1, or they are between, 1 million minus 1 and 1 million plus 1, it doesn't make any difference to softmax. It's going to make a numerical difference when you compute the exponential, but that's a different story. In fact, PyTorch is smart about this. It's not going to blow up. So that's a really important property. And that's quite interesting. So now the soft min function I was telling you about. So this is why it's called softmax, right? Because basically, and that's why it should be called soft argmax, because basically it tells you which of the values in the list of values is the largest one. It gives it a value close to 1, and then it gives the other values a value close to 0 with some smooth transition. If you want a non-smooth transition, you can apply softmax to x, which you multiply by some coefficient beta, right? So for a very large value of beta, which would be a coefficient that you pick, which you can learn also if you want, but you can set it. For large values of beta, the transition between 0 and 1, when x grows larger than one particular component grows larger than all the other ones, would be very sharp. Okay, so set beta to 1,000 or something. If one x is only slightly bigger than the other x's, its softmax output would be 1 and the other ones would be 0. Okay, for a small value of beta, you're going to have a smooth transition. As you increase one of the x's relative to the other ones, you're going to have a smooth transition between 0 if that component is much smaller than all the other ones, to 1 if it's much larger than all the other ones. So softmin is just softmin of x is just softmax of minus x. Okay, so that's the generalized form, right? Which when you have a beta, and that kind of takes care of negatives versus positives and stuff like that. So if beta is negative, you're going to have a negative in front, which may or may not be what you want. Right. So for the same reason that I told you that if you want to take the log of a function like this, you better do it in one fell swoop rather than sort of computing the function and then taking the log, because you might have very large numbers, in between. And particularly when you backpropagate gradient, you get essentially zero gradient or infinite gradients. You backpropagate gradient to a softmax, you will get if one x is much larger than the other ones, you basically the softmax basically saturates. So when you backpropagate, you get gradient 0. And it could be that the log of the output of the softmax is close to 0. When you take the log, you get something that basically is minus infinity. So when you do everything in one fell swoop, you don't have that numerical problem. There's a trick inside of PyTorch, and the trick is that you kind of reduce this computation of the softmax by first computing the max over the xi's, and then you can factor what goes on inside and solve the numerical problem. So log softmax is probably one of the most important modules inside of PyTorch. It's one that's used universally for classification. Okay, when you build a neural net, you use the log softmax module essentially as a cost function. You don't use directly as a loss function, but it's basically the main component of a loss function. So what does that do for you? So as I said, the softmax itself turns the values, the scores coming out of the neural net, whatever they are, into a bunch of numbers between 0 and 1 that sum to 1. And then you take the log of that, and you're back in the same space as the original x inputs, basically, because the log kind of cancels the exponential. But what you have done is that you've removed the absolute values of the x's. So as I said, softmax really cares only about relative values of x's. And so now what you have is a bunch of scores that really indicate the relative values of the x's without caring about their absolute value. And that's very important if you want to build a classifier, and the classifier has multiple categories. You need to have some competition between the different categories, because an image, can only have one category, okay, if it's a mutually exclusive categories. And so what you'd like is you like scores that, basically are like probabilities and kind of inhibit each other, right? If one category has a high score, the other one should have low score, and that's what the softmax normalization does. But then why do we need the log? Okay, so so I guess it's time to talk a little bit about a particular type of standard classifier architecture, right, of neural net. So you would have an input X, an image, audio, whatever it is. Think of it as it would be a multi-dimensional array of some kind, but we're going to think of it as a vector. Then we'll have, multiple layers of modules, whatever they are. I'm not going to specify here. It doesn't matter. In a standard neural net, again, they're going to be, linear modules and ReLU modules. The last one being a linear, not a ReLU. And then we're going to put one of those softmax module. Okay, and this output, which is the predicted output, is really going to be a vector of numbers between 0 and 1 that sum to 1. Okay, so I'm kind of redrawing this softmax module here. Okay, in comes a bunch of numbers that come out of the linear module that's before. Out come a bunch of numbers between 0 and 1 that sum to 1. So if you want to train this to classify it as a classifier, what you want is you want to train the system in such a way that the output for the correct class is close to 1, and the outputs for the incorrect classes are close to 0. So what you can use is a cost function. So basically, the output here is going to be, 0.1, 0.2, 0.6, and 0.1, okay? And let's say the desired output is something like 0, 1, 0, 0. So first of all, your system got it wrong because it gave the highest score to the third category, and the correct category is actually the second one, not the third one. So what we're going to need here is some sort of cost function that measures the divergence between those two things, okay? I don't want to say the distance because this may not be a distance, but some measure of discrepancy between those two things. And that's, again, one of the most important modules we're gonna use. So one cost that we could use is squared error, okay? So squared error says, I'm going to just compute the sum of the square of the differences between the value I get and the value I want. And that might work. But in classification, people use something called binary quotient. And that involves log softmax, okay? So before I go there, I want to tell you something about this. so what happens here is that all those numbers compete with each other, right? Because they are normalized by their sum, they compete with each other. So if the network wants to increase the value of the second output here, which is the correct one, it will have to decrease the other one because it's normalized. Okay, and that's the advantage of softmax for kind of mutually exclusive for classification mutually exclusive classes. I want to maximize the negative log of the correct output. So this target here 1 says I'm just going to if we want to translate this into an objective function, it's going to say I want to pull this value up, and as a side effect, the other values will be pulled down because it's all normalized. So I just want to make this large. Okay. And what am I going to use as a loss function to make this value large? The answer is I'm going to use the minus log of it. Okay, so those are the y bars. Okay. So my objective function, which I'm going to minimize, is the minus log of the activation coming out of the softmax of the correct output. Okay, so C here indicates the correct class, the correct category, the desired category, right? So in this case, it's index. It's the second one, which is index 1, right? Because we start at 0. So here C equal 1, because it's the second output. I want to make this output of the softmax as large as possible. And the way I make it as large as possible is that I plug it into a loss function that is the negative log of this output. And if I minimize this negative log, I'm going to maximize the YC, the 0.2 is going to get bigger. And as a consequence, the other ones are going to get smaller because it's normalized. Okay? That's why I need to compute the log softmax. That's because it's going to get into my loss function. So the log softmax of the correct category, minimizing the negative log softmax of the correct category, is the main way to train a classification system in deep learning. That's what most people use. I'll come back to this in a second. Okay, so that's why log softmax is so important. And in fact, we're coming to cost functions. So those are things we stick on top of a neural net to tell us whether the neural net is doing something good, or a deep learning system to tell us whether it is doing something good. The most common one is the squared error. So the squared error is simply the square difference between the output we want and the output we get. And they're using different notations here, and they're doing it over a batch. So this index 1 to n is index over a batch. And you compute either the sum or the mean. You can choose with this sort of reduction parameter. Oops, sorry. Whether you compute the sum of the mean over the batch. Oops. But what you do is you compute the square difference of each component. Okay. So very simple. Whatever comes out of your neural net is a bunch of outputs. The cost function is the MSE, mean squared error. You get desired values. Okay, so let's call those the yi bars, and those are the yi's. Okay, this is different notation from the one used in the PyTorch manual, and you just compute 1 over, I don't want to call it P, actually. I don't want to call it N either. K, which is the number of outputs here. Sum over I of yi minus yi bar, which is the output of the network squared. Okay. Or you can just write this as 1 over k square norm of of y minus y bar. Okay, so it's really the Euclidean distance averaged over components. So if you're doing regression, so basically if your neural net is trained to produce continuous values of some kind, not classification, but regression, that's a perfectly good cost function to use. Okay, very simple. This is the same thing, but instead of the L2 norm, we use the L1 norm. So this is the sum of the absolute values of the difference. Not used very often, but used sometimes. Variants of this, which I'm not going to go into the details of. And here is the negative log likelihood loss, which is a special case of which is the log softmax I was talking about earlier. Okay, so we have a target category. So we want to use this for classification. We have a target category, and which is this little c here. And we want to make the output of the correct category as large as possible and the other ones as small as possible. And if the outputs come out of a softmax, we can reduce this into a single function, which is the log softmax, right? So I explained that earlier, right? We want to make the correct output as large as possible. And the way we do this is by minimizing the negative log of it, okay, which is negative log likelihood, if you want, of the correct category. But if we do this as two separate modules where we compute softmax and then we have negative log likelihood, we get numerical issues. So what we do is we compute the log softmax and then we just maximize the correct output, or the negative log softmax and then minimize the correct output, which is the same. And that can be seen as a special case of the cross-entropy loss. So here is the expression for the softmax, and this is the negative log softmax, which is a negative log likelihood loss applied to a module with softmax, right? Where the last module is softmax in one fell swoop. So I can develop this if I take the log of this exponential, right? So the log of a ratio is the difference of the logs, right? So I can write this as log of the numerator minus log of the denominator, right? Now the numerator as log of exponential which cancel each other, so I just get the score of the class with a minus in front. Okay, so this is the first term. And then the second term is the so-called log partition function, which is the log of the denominator, or minus, the log of the denominator. So the overall objective function is something like this. It says, make the score before the softmax of the correct class as large as possible, because you have this minus sign. Okay. And then make the log of the sum of the exponentials of all the scores, including the correct one, but with all the incorrect one, as small as possible, which means make those scores as small as possible, as negative as possible. Okay, so the reason why this is interesting to look at is because this is going to be the gradient you're going to get when you backpropagate gradient of a negative log likelihood loss through a softmax, through a log softmax in that case. This is the kind of gradient you get with respect to whatever variables enter the softmax. Okay. So to minimize this, you need to minimize the first term, which means make the x of the correct class as large as possible. Okay, so make the score of the correct class as large as possible. Simultaneously, make the scores of all the classes as small as possible, including the correct one. So the score of the correct class is going to get pushed down simultaneously with being pushed up, but it's going to get pushed up by this term much stronger than is being pushed down by that term. And we'll see why in a minute. So you're going to get the desired effect in your neural net, going down, which is that the correct class is going to get pushed up, and incorrect classes are going to get pushed down. The scores, if you want. So there are various tricks because people want to use softmax with a very large number of categories. So, for example, let's say you want to train a spell corrector or a language model. So something that will predict, you type an email and this thing is going to predict what word you're likely to type next. What you need is a language model, which is something that will, basically predict a probability distribution of all the possible words in the language you're typing in. It's going to look at your previously typed word in a text, and it's going to predict what word comes next, so that it proposes you the most likely one coming out of that model. A more useful utilization of those language models is you're doing speech recognition or handwriting recognition or something like that, or text generation. And the system doesn't have perfect identification of the words. And what you want is a language model to correct the mistakes, okay, of your recognition system. So that's called a language model, a probabilistic language model. And the problem with this is that you need a system to produce a probability distribution over a very large number of categories, because the number of possible words in the English language is, the most common words is like 100,000 or something like that, right? And the full dictionary is more like 300,000, if not more. So you need to do a softmax over 100,000 variables, and that can become kind of expensive. Sometimes you might need to do a softmax over 1 million entries, and that's kind of numerically unstable and expensive. So there are tricks to kind of do this fast by basically ignoring the things that have low scores, and that's one of them that you're welcome to use. I'm not going to go into the details of how this works. So here is another kind of loss that can be used for classification as well, and it's called a margin ranking loss, or ranking loss with a margin. It's basically a difference, addition of a constant, and then a value. Okay, it's as simple as that. You can see the formula at the bottom. And what it says is that if I have a network with multiple outputs and 2 scores come out of the system, I know that the correct category is one of them, and I want to make sure that my system produces the correct category. So what I want to do is I want to make the score of the correct category as large as possible, not as large as possible, but I just want to make it slightly larger than the second highest scoring category, right? So that's called a ranking loss. So you have a neural net. It may have 10 or 1,000 outputs, and what you're doing is that you're saying which output is the correct one. Okay, I want to make that big. Which output is the largest one among all the outputs, whether it's the correct one or incorrect one, I don't care. Let's say it's another one. Okay, maybe its score is higher, maybe it's lower, I don't care. But what I want is I want to make sure that the score of the correct class is larger than the score of that other class that has a high score by at least some margin. So I can use this loss, okay? I pick x1 and x2 as being the correct one and the most offending incorrect one, for example, right? And I push the first one up and push the second one down in such a way that the difference is at least some margin. And so now I'm guaranteed that if my network, learns properly, then the correct category will have a higher score than all other categories by at least that margin. Okay. So that's another one of those losses that only cares about differences, doesn't care about absolute values, only cares about differences between scores. But it's not like softmax because it doesn't take into account the entire set of outputs. It only takes a pair. So architectures really are different ways of arranging modules to build neural nets. Any question at this point, by the way?
We've been covering, answering questions on the chat on the fly.
Awesome. Thanks. Okay, we'll jump right in. Okay, so we've talked about linear modules. We've talked about pointwise nonlinearities. We talked about softmax. We've talked about a few cost functions: least square, mean squared error, and negative log likelihood applied to softmax, which gives you the log softmax, right? But here is another set of modules that are quite different from what we just talked about. Those are kind of quadratic modules, if you want. Okay, so here's an example of quadratic module. It's a module where the output, the ith output, is a weighted sum. So here, this is a linear module, right, where we compute just a weighted sum of inputs. But here, what we're going to do is that our weights themselves are going to be functions of other inputs, okay? So we're going to have a linear module here that takes x, multiplies it by a matrix, and gives us, an output vector. But the matrix itself is not a set of parameters. It's the result of applying a linear function to a bunch of to another vector z through another matrix u. Okay. So the overall thing. So we're gonna write each wij in our linear module as itself as a weighted sum, basically, of individual slices of a three-dimensional, a third-order tensor, right? A three-index tensor, uijk. So this is a multi-dimensional array with 3 dimensions. And we multiply each slice of that tensor by a coefficient, which is a component of zk, the vector zk. That gives us a matrix. And that matrix is wij. And we use that matrix wij to multiply the vector x. Okay? So overall, I can write it down this way. Si is equal to sum over j and k of uijk, this kind of three-dimensional tensor, times zk times xj. This is a quadratic form, right? So basically things, imagine z is equal to x. This would be kind of a quadratic form. But it's basically a second-degree polynomial, if you want, a monomial that's function of x and z through those coefficients. Right? Okay, so that gives us a lot of power because it allows us basically to have a little piece of a neural net whose function is determined by another piece of the neural net. It allows us to have switches. It allows us, for example, let's say if x is a vector with a bunch of components, we could design this whole thing in such a way that depending on z, certain components of x would be selected in the weighted sum, and some components of x will not be selected in the component by setting some coefficients in w to 1 or 0. Okay, and that's basically what attention is. So you might have heard by reading various things about neural nets that there is this mechanism called attention. It's probably a bad word. What it means is using multiplicative interactions to switch in and out certain variables in a function that you apply, so that the network pays attention to the variable you switch in and doesn't pay attention to the one you switch out. Here's a special case, which I'm going to explain here. And that special case is a switch. Okay, so let's imagine we have a module that has 2 inputs, x1, x2, and a single output. I'm going to call it S. And depending on some other variables, which I'm not going to specify, this guy either chooses the first variable or chooses the second variable. Okay, so we can move this switch to select x1 or select x2, right? And a module like this, so the switch module, you can think of it as a special case of this product module where the W matrix is either, well, it's not a matrix, it's a row vector, right? So W is either equal to this or is equal to that. Okay, and I want to multiply this by x1, x2. Here I get x1, and here I get x2, right? So if I have some other variable here, which I call z, which is a scalar, or is, not a scalar, a vector with 2 variables, two components, z1, z2. And I can write if Z1 equals 1, I get this matrix. Is Z2 equals 0. And then if Z1 equals 0 and Z2 equals 1, I get that matrix. Okay, that would be a way to write the U. The U matrix would be a matrix with those two rows, essentially. And the Z vector would select one row or the other, depending on whether it's 1, 0 or 0, 1. And that's like a switch. Now, here's a very interesting thing about the switch. It's very easy to backpropagate gradient through a switch. Essentially, imagine the switch in the first position, so it selects x1. What that means is that when I wiggle x by some value, s is going to wiggle by the same value. When I wiggle x2 by some value, s is not going to wiggle at all. What that means is that if I get a gradient of some cost with respect to s here I just copy it. So when I backpropagate through it, I get the same gradient here. And here I get 0. If the switch is in this position. Okay, if the switch is in the other position, I get the opposite. I get 0 here, and I get dc over ds here. So it looks like a switch is an inherently non-differentiable thing, but it is differentiable with respect to its inputs and outputs. It may not be differentiable with respect to the z, unless you use kind of a linear way of writing it, which I did here. Okay, so backpropagating to a switch is very simple. Remember the position of the switch, and then just copy the values, the gradient from the top, with respect to the top, to the inputs that are switched in. Okay, but here's a slightly more interesting form of this attention module, which is probably the most common one, and is to basically make the coefficients coming out of make coefficients basically that sum to 1 to kind of switch either one slice of a U matrix or another slice, which I write here, W1, W2. So think of W1, W2 as slices of this U matrix, and think of the Z's here as the result of a softmax, and you get this kind of module, and it's probably a more convenient way to write it. So here, I take an X, I multiply it by some matrix to get W1X, and I get S, and then I have another branch where I take X2, multiplied by another matrix, and I guess sum the two results, I get this S, right? So this is a weighted sum of two inputs multiplied by two separate matrices. This could be the same input, by the way, okay? Doesn't matter at this point. And what I'm going to do is that I'm going to make those, sorry, in this case, this is for scalar values. So W1, W2 are scalars, okay? And here I'm going to make W1 and W2 the outputs of the softmax. So the softmax has two inputs, two outputs, and the two outputs are between 0 and 1 and sum to 1. So I get two weights here that are between 0 and 1 and sum to 1. Okay? So what you get here as S is a weighted sum of x1 and x2, where the weights are two weights that are between 0 and 1 and sum to 1. And so if one of them is 1 and the other one 0, as a consequence, I only get x1. And if it's the other way around, I only get x2. But for intermediate values, I'm going to get something in between. Okay, so what this module is going to do is it's going to be able to softly switch between paying attention to x1 or paying attention to x2 by either copying x1 into S or copying x2 into S, or copying some sort of weighted sum of the two, depending on the value of Z. Okay, so Z is a way to basically control the attention that the system will pay to either x1 or x2. And that turns out to be not only very useful, but basically universally used as a basic module in most natural language processing systems, and increasingly also in vision systems. A slightly generalized form of this. Is that clear? Any question at this point?
No, so far everything's fine.
Cool. So think of this as a soft switch, right? I told you here about a hard switch, okay, that just picks one of the two inputs. This is one that softly picks one of the two inputs and kind of linearly interpolates between them otherwise. And an interesting application of this is what's called a mixture of experts. Some of you may have heard of the latest gigantic model by Google, an enormous NLP system with 1 trillion parameters. It's 1 trillion parameters, but it's actually one of those mixture of experts things. So not all the parameters are used all the time. So let me explain what this is. Let's imagine that you have either a single set of inputs or two different inputs here, but let's say it's a single one, X1 and X2 are the same thing. We'll have two separate neural nets here, which I'll call expert 1 and expert 2, two separate deep learning systems that perhaps are expert at a particular type of input, each of them, but not the entire thing. So let's say both X1 and X2 are equal, and X is spoken language, let's say, and we want to do speech recognition. But one of our experts can, understand Catalan, which is a language in northern Spain and southern France, and the other expert understands Provençal, which is a dialect of kind of southern French dialect, if you want. Those two languages are actually very similar. They're also similar to Italian, actually, and Spanish and French, but French has more German in it. Okay, so some speech comes in, and you don't know if it comes from someone from Provence or someone from Catalonia. So what you want is, to switch in the correct speech recognition system, but you need something to decide whether it's Catalan or Provençal. And so you have another network here that looks at the same input, perhaps, or maybe a different input, but maybe the same input, called a gator. And that gator decides, it's got two outputs here in this case, and the two outputs are, 1-0 if it's Catalan and 0-1 if it's Provençal, or somewhere in between if it doesn't quite know, because many words are very similar, and you can tell in the first few words, which one it is, maybe, or the pronunciation are really similar. So that softmax thing will basically decide on weights with which to combine the two experts so as to make a decision. And initially not knowing which language this is because they are so similar. You can reuse this example with your local dialects, okay, which probably are better examples than Catalan and Provençal. So that's called a mixture of experts. You can have as many of those experts as you want. And basically it says, I have, multiple specialized experts, and I have a gator that decides in which part of the space each expert is an expert at, okay? And it decides to switch in the correct expert at the right time for the current particular input. So let's take a very simple version of this here to kind of visualize this a little bit. Let's say that we have, our input vectors are points in a plane, okay? And category 1 is this. And category 2 is that. Okay, so ideally, let's assume our experts are linear classifiers. Okay, so a single layer neural net, basically. What we'd like is one expert to tell us in this part of the space which category is blue, which one is red, and another linear classifier to tell us in this part of the space where is blue, where is red. And then what we need is the gator system to tell us. So that's going to be another linear classifier. And in this part of the space is going to tell us use expert 1. And in that part of the space, it's going to say use expert 2. Okay, so very simply here, with a mixture of experts, you can do nonlinear classification with 3 linear classifiers in parallel, one of which decides which of the experts is the proper one to use. Okay, so this is the discriminative surface from the gator. And this one is for expert 1, and that one is for expert 2. But this is not limited to this. You can have huge networks in those experts. You can have modules of this type inside of a network if you want.
Can you tell us about that Z, which is gray? So it's an observation.
In this case, it's an observation. So here in the example I just showed, I just drew, you basically have only one variable X. Okay, and it goes in parallel to the gator, to expert 1 and expert 2. And then the gator has 2 outputs. Those 2 outputs are weights between 0 and 1 that sum to 1. So you multiply the outputs of each of the experts, which are vectors, by those two things. And you sum up the results. Okay, so that's the overall architecture. But this block is this, right? Where you have a softmax here inside. Okay, and this is Z, this is X1, and this is X2. Okay, but in general, so I use it here, a particular example where all 3 inputs are the same. But in general, that's just a module you can stick in your network and do whatever you want. Because you can have as many experts as you want.
So it's the softmax of what?
Well, so softmax is a module that takes a bunch of inputs, produces a bunch of outputs, right? So in this case, it takes 2 inputs and produces 2 outputs. And so whatever your gator is, you transform those outputs into a bunch of things that are between 0 and 1 and sum to 1.
And the final question is going to be, and how do you train this gator? Do you train it separately or?
You just do backprop. You don't have to worry about it. Just backpropagate gradient through this. Okay.
So the question is, how do you do backprop?
You don't have to think about it. You just write this, right? You could try to be smart about it, but the best thing is to not be smart about it and just propagate gradients, right? This is a graph, as we've written a few other graphs. Okay, let me draw this, right? So this is whatever. This is a neural net of some kind. This is another neural net of some kind. This is another neural net of some kind. Doesn't matter what kind. Okay. And then here, okay, so I'm writing this explicitly as multiplications, but really this is sort of a multiplicative module of the type that we talked about. Okay, and it's just an addition. Okay, and you get some output. Let's call it y bar. You plug this to a cost function, which takes the desired output y. Right. Now I can encapsulate this into a single module. Doesn't matter. What I'm just telling you is that there needs to be a softmax at the output, but it's just an architecture, whatever it is that you want. So how do we backpropagate gradient? We don't have to think about it. That's the cool thing about automatic differentiation and PyTorch and all those things, TensorFlow and all those things. You just write your module this way. Okay, you say My output is the sum of this variable multiplied by that variable plus this variable multiplied by that variable. Okay, and that variable, those variables are equal to softmax, computed from Z through some neural net. And those two variables are computed with F1, F2. So you just write this, right? You just write this as a function, as a program. It's a few lines, right, in PyTorch. And automatically, PyTorch will figure out how to backpropagate gradient. So basically, it's going to say, okay, I'm going to get some gradient here of my cost here, dc over dy bar, right? Which is going to be some value. Here, because this is a plus module, when you backpropagate through an addition, you basically have to copy the gradient on both inputs. So here I'm going to get dc over dy bar, the same value. It's going to be the same value copied. When I backpropagate through a multiplication by a value, let me call this W2, here I get W2 times dc over dy bar. Here I get, if this is W1, here I get W1 times dc over dy bar. Okay? And then I take those, this is a vector, I backpropagate it through the network, and we've already seen how we backpropagate through neural nets, right? So, it's going to happen inside here, doesn't matter, and you're going to get a gradient with respect to the weights of this guy, which I'm going to call, I don't know, theta 3, theta 2, and this is theta 1. Now, to backpropagate through this branch, it's the same thing. What I'm going to get here, so let me call this Z3, Z2. Okay, so the gradient I'm gonna have here is going to be equal to Z3 times dc over dy bar, because I have a product of two variables. So when I have a variable equal to the product of in this case Z1 and Z3, okay, when I have dc over dz1 is equal to dc over dy, which is I shouldn't call this y. I'm sorry. I should call this something else because it's going to get confusing. Okay, so this would be this variable here, which I'm going to call v. Okay, v3. Right. So v3 is equal to z1 z3, right? Because, well, it's equal to w. I'm being extremely confusing here. W2 z3, and again, my numbers are horrible. So when I differentiate a product with respect to the first variable, I get dc over dv3 times dv3 over dw2, and that part is the derivative of this with respect to w2, and that's equal to z3, right? So I get dc over dv3 times z3. And if I now differentiate with respect to v3, going through the same process, I get dc to z3. I'm sorry. I get dc over dv3, which I know, times w2. Right. So if I have a gradient here, which is dc over dv3, when I backpropagate through this product, in this branch, I get the product of this gradient by this weight. And when I backpropagate through this branch, I get the product of this gradient by this value, which is that. Okay? And it's just, simple derivatives. So then you will get a gradient with respect to those two outputs. At the output of the softmax, you backpropagate through the softmax and then backpropagate through this other function. But you don't have to worry about it. PyTorch is going to do it for you. So here's an exercise. Interesting exercise, which I think will help you understand a lot of things. Let's say we have a softmax module, okay? So Zi equals e to the beta xi divided by sum over j of e to the beta xj, okay? Let's assume that I know dc over dzi, okay? Compute dc over dx, k, for any k. Okay? All those guys are known. What are those guys? Right? So what you can write is that they're going to be equal to d to sum over I of dzi over dxk times dc over dzi. Okay, this is chain wall, right? We explained this last week. And the question is, what is this? So this is a Jacobian of the softmax. Okay, it's a matrix. JIK. For each index each pair of index IK has the partial derivative of the ith output of the softmax with respect to the kth input of the softmax. And it's a very good exercise to compute this, okay? I very much encourage you to do this. It's very easy to find the solution. You can find this in, various places on the web, but it's much more fun to actually figure it out by yourself. You'll learn something by doing it. And we tell you how do you backpropagate through a softmax, okay? Okay, here's something a little more complicated, as if that wasn't complicated enough. And it's reparametrizing the parameters. So this is kind of a bit of a slightly more general way of kind of instance of what I was just talking about of products, product units, where weight matrix is the result of weighted sum of slices of a tensor. So here I'm sort of making this a little more general. I'm saying, imagine that we have a network G of X and W, but the W's are not parameters that we can adjust. They are themselves the result of applying a deep learning system to a set of more elementary parameters, U, elementary variables, U, okay? So this is an example of a neural net whose weights are the output of another neural net, if you want, okay? So this looks like a totally hairy thing, but it actually used very, very commonly, and in very simplified forms or in more general forms. And again, it's interesting to understand how that works, but in the end, PyTorch takes care of that for you. So we have a neural net here, takes an input, applies some complex deep learning system to it, G of XW, or maybe it's simple. You get an output prediction, Y bar. plug this into a cost function of some kind, log softmax, whatever, with a desired output, okay? But then the W is another input to that system. It's not an internal parameter. It's another input, another variable. That is the output of some function HU that itself has inputs or parameters that we're going to learn. So these might be either learned parameters or inputs from some other source, okay? Let's say they are learned parameters, which is why I circled them in red. Okay, so when we backpropagate gradient, we have a gradient of the cost function with respect to y bar. We have two Jacobian matrices here for g of xw. One of them is going to give us the gradient of g of xw with respect to x, which we don't care about very much. And the other one is going to give us the gradient of g of xw, of the gradient of the cost function with respect to w. Okay, so that gives us, let's assume we interpret w as a vector. It could be a matrix or a tensor, but it doesn't matter. We interpret it as a vector. And we're going to get a gradient vector of the same dimension that indicates the partial derivative of c with respect to all components of w. And then we're going to backpropagate that through h. And that's going to give us gradients with respect to u. Okay? We can make an update of u using this. So because the gradient with respect to u is the product of the Jacobian matrix of G with respect to W and the Jacobian matrix of U with respect to U, we get this formula, okay? So U is updated by a quantity here, eta times the gradient of the cost function with respect to W times the Jacobian of H with respect to U, okay? This is the gradient of W with respect to U really. So this is going to result in a update of U, and we can think of this as an update on W. And because W is a function of U through this H function, we can compute what the update on W will be, and it's basically the update on U multiplied by, to which we apply H of U. But if the update is infinitesimally small, then the update will basically be the Jacobian of H again. So the implied learning rule on W, okay, which is just something we can look at without really worrying about it, because as I said, PyTorch takes care of this. This is just backprop. There's nothing more to it. But if you want to see the equivalent result of doing gradient descent in U, what effect is it going to have on W? It's going to have this effect. So it's as if we would apply a gradient-based learning rule to W, where the gradient update would be compute the gradient of the cost with respect to W, and then multiply this gradient by this big matrix here, which is the Jacobian of H multiplied by its own transpose. So this is a positive semi-definite matrix. And then multiply that by the step size. Okay? And in gradient descent, if you multiply the gradient by a positive semi-definite matrix, you're still doing gradient descent. It doesn't make any difference to the fact that you're doing gradient descent. So basically, you're doing gradient descent in U, but as a side effect, you are actually doing gradient descent in W, just with a different direction, where the gradient is transformed by this matrix. This particular point we'll come back to in a few weeks when we talk about optimization. But the whole idea of this, having the weights function of another thing, that's used a lot. Here is an example where it's used, weight sharing. So let's say that h of u is a very simple function that takes a single variable u, a scalar variable, and duplicates it into multiple copies, right? So it makes it into a vector where all the components of the vector have the same value. Okay? So essentially, we have some sort of big network here. It goes into a cost function of some kind. And here we have a single variable u. And we have a module, which is basically a duplication module that just copies that variable u into multiple copies of itself. Okay, it's a Y cable, right? You need to, connect your multiple headphones to your music player, right? You need a Y cable. Okay, so it just copies the signal. Here I say that U is and I'm going to call this W, this collection. So to get the gradient of the cost function with respect to U, what do I need to do? In other words, how do you backpropagate gradient through a module that does nothing but just copy a bunch of variables? Okay, so let me take a very simple example. And Z1 is equal to U, and Z2 is equal to U. Okay. So if I have the gradient of some cost function with respect to Z1, what is going to be the gradient of this cost function with respect to U? And the answer is the sum of those two gradients. Why is that? Okay, it's very easy to understand. First of all, it's a direct consequence of the general form of chain rule, which I wrote last week, which is that if you have a variable that influences multiple variables, the gradient of some cost function, some subsequent cost function with respect to this variable is the sum of the gradient with respect to each of the variables that it influences times the derivative of each of those variables with respect to itself. And this is just a special case. Why is that? If I perturb U by delta U, it's going to perturb Z by delta U and Z1 by delta U, and Z2 also by delta U, right? So as a consequence, C, the delta C is going to be equal to, I'm going to write it this way, is going to be equal to dC over dZ1 delta Z1, which is delta U, plus dC over dZ2 delta Z2, which is also delta U. Okay. And so now, I'm going to write those deltas as d's, really. I mean, there are infinitesimal quantities. So I can divide both sides by du. And I get dz over dz1 plus dc over dz2. Okay, so a module that divides, that copies a variable into multiple copies. When you backpropagate through it, you just compute the sum of the gradients. It's as simple as that. Okay, so in this little example here, if I get a vector of gradient of the cost with respect to W, I just sum them up and I get the gradient with respect to U. Right? So dC over du equals sum over I of dC over dWi. Very simple. But again, PyTorch is going to take care of that for you. Why am I telling you this? It's a very interesting special case. And this is a preview of basically the trick that's using convolutional nets, which we're going to talk about next week. So let's say we want a system to detect a motif. Okay, so detecting a motif might mean detecting a face in an image, for example, or detecting a particular key phrase in a speech sentence. So let's say you are Amazon or Google or Facebook, and you're supposed to detect. You're supposed to have a very simple neural net that just listens to the speech signal and detects "Hey Google," or detects Alexa, or detects "Hey Facebook" or "Hey Portal." Now here's the thing. I just said, "Hey Google," and of course my phone woke up. Or you want a phase detector and you have, an image, and basically you have a little neural net that you train to be a phase detector, and you like to apply it to every location in the image, right? But you like to train it in that situation where you don't necessarily know where the phase is. Or you are, I don't know, you're playing in the stock market and you want to detect a particular motif in the variation of a set of financial values, regardless of when they happen in your sequence. So what you need is a neural net that looks at a set of inputs, a piece of an image, a segment of a signal, whether it's speech or financial values or whatever it is. And you need to kind of slide it over your sequence of inputs, and basically, your detector to kind of turn on wherever it needs to be turned on. And you can think of this as essentially different copies of the same neural net that all share the same weights. Okay, so you have one weight vector that is used by all of those neural nets. But when you're going to backpropagate gradient through this, each of those neural nets is going to contribute a gradient to whatever objective function you're minimizing. Okay, and the way to compute the gradient, the overall gradient with respect to W, is just to sum up the individual contributions of the gradient from each of those instances of those replicas. Okay, so this is nothing more than an example of this kind of fan-out Y connector, where one set of variables is used multiple times. And because it's used multiple times, when I backpropagate, I'm going to get multiple gradients for each of those multiple times. I sum up those gradients, and I get the gradient with respect to that variable. Is that clear? Questions?
No questions. Actually, we are out of time, actually.
We're pretty much out of time, yes.
Yeah.
But that's pretty much where I wanted to be. So
that's great. So we see everyone in class tomorrow for the PyTorch part, where we're actually going to be using PyTorch finally for training a network, and you will see how running backprop is very easy. And we will be releasing the homework right after the lab, such that you have actually all the knowledge to start working.
Right. And so remember the exercise I gave you here, computing the backpropagating through softmax. It's a good exercise.
Yeah, I've been writing on the chat that those exercises you're giving are very encouraged.
Right. I'll put the whiteboard, PDF version of the whiteboard on the drive, so you have record of it.
Okay, thanks. That's great. All right. See you, everyone. Bye-bye.